coefficients in Farey fractions.
And you hear me? What? You may regret it. Okay, so what I would like to talk about are products of binomial coefficients and Farey fractions, but first a brief appreciation of Neil. We worked at Bell Labs and AT&T Labs for 25 years together, not in the next office. I wrote one paper with him, at least, on integer sequences. 2, 4, 8. Okay, so, to Neil, thanks for OEIS. I use it often. Thanks for demonstrating how to do research and exercise at the same time. Also, thanks for taking me rock climbing exactly once. Remember, a hero dies but once. A coward dies 1,000 deaths. So who has the more exciting life? Okay. And thanks for being continuing inspiration to write things up and get things done. Of the material in this talk, I would talk about a paper posted on the archive last month with Harsh Mehta with the same title. There's a sequel paper which is in preprint form, and there are ongoing follow-up projects with Juan Arias de Reina and Bob Vaughn. And Harsh Mehta was my RU student in 2013, and he came with very strong recommendations. And so this, with him, I was able to complete a long-running project. And that project concerns the behavior of Farey fractions, which I will get to a little later on. And in the process appears the following integer sequence: the products of the binomial coefficients in the nth row of Pascal's triangle, which is product n choose k. So there's some data, and if you use this data, you won't have any trouble identifying it in the OEIS. It grows rather rapidly, like e to the constant n squared, roughly the size. And in this talk, the problem I'm interested in is understanding stuff about prime numbers. And one way you can prove things about prime numbers, the Chebyshev estimates of prime numbers make use, for example, of binomial coefficients or related things. So we can measure the size of these numbers Gn as real numbers, and the scale I'm going to use is the logarithm. So G infinity will be the logarithm of the value of the binomial coefficient product. And what is interesting is you can also look at the prime factorization of these numbers. So I will let order P of Gn will be the exponent of, will be the number of powers of the prime P that divide Gn. So we have a formula which says that Gn factorizes as P raised to this little Gp event. And if you take the logarithm of both sides, then you get a formula relating these two quantities. You get log Gn bar is equal to the summation of the exponents for each P times log P. So what is interesting here is that certainly Gn is divisible only by primes up to n, and they're raised to various powers. But if you study the individual functions Gp of n, these are oscillatory functions that go up and down in a weird way. And then, as I said in this slide, if you study the behavior of this function for a fixed prime, you see interesting oscillations in divisibility. And explaining this behavior was one of the motivations for this work. And a second motivation came from products of Farey fractions, which is actually, this is a spin-off. So here's a picture of what the divisibility for P equals 2 looks like. So if you look at this picture, you will see there's a lot of structure in there. You see a bunch of, first you see little blocks. The blocks are at powers of 2. So there's there's some repetitive behavior that's occurring at each power of 2, and then as the scale of things increase, because these numbers are getting larger, the scale of the repetitions increases. You see these stripes. You see a stripe pattern. So how can these stripe patterns be produced? The oscillations have to go up and down wildly in order to fill in all of these stripes, because they're being sort of produced in a continuous way. Also, so here are comments on that graph. The function is somehow increasing in some average size, and it has this regular series of stripes. The stripes are grouped by powers of 2. Maybe there's a self-similar behavior in there. The function has to be oscillatory to produce those stripes, and it's a little harder to see in the plot, but the number of stripes increases by 1 at each power of 2. Let me go back. The stripes are not all the same size. So you'll see some points, the top stripe, 1 point there you see, and then you see more and more points at each level, and then a reverse behavior. By the way, the value 0 is attained. The value is attained. Okay, so now I would like to say something about the motivation. So the Farey fractions of order n, if you're a number theorist, then you know these are simply the fractions in lowest terms between 0 and 1 that have denominator bounded by n. So there's F4 there. Now I got interested a few years ago in the question of extracting a statistic from the Farey sequence that consists of just the product of all the Farey fractions. Well, that's kind of uninteresting because that product is 0, because 0 is a Farey fraction. So we throw that one out, and then we get the product of the non-zero ones. And if you do that, the number of non-zero Farey fractions is a nice number theoretic function. It's capital phi of n, which is the sum of the Euler-Totient function from 1 to n. Now, the distribution of the Farey fractions is related to the Riemann hypothesis. If you take the Farey fractions of level n and you put a delta function in each Farey fraction, then this is a measure. You scale it by the number of Farey fractions, you get a discrete measure on 0, 1. And that measure, as you go to infinity, converges to the uniform measure. This is well known. What's less well known is the Riemann hypothesis is related to the rate of convergence in distribution of these measures. This is encoded in a theorem of Fresnel proved in 1924. And then extended by Landau and various other people. It's been studied rather extensively for the last 70 years. Okay. So if you consider the product of the Farey fractions, that is sort of sampling. That is sort of sampling the Farey fractions with respect to a measure that's not the uniform measure. It's a measure scaled by the logarithm. If you take the logarithm of this number, then you're taking an average of the logarithms of the Farey fractions. But it turns out this Riemann hypothesis encoding is not very sensitive to the particular measure, and people proceeded to prove more and more theorems that you still got the rate of convergence was fine for lots of different measures, and finally they covered the logarithm in 1952. So the Michaelis theorem in 1952 shows that this single statistic all by itself encodes the Riemann hypothesis. If you let, and it will be convenient later on to use the reciprocal. This is just, I prefer to have a big number rather than a small number. If you take a product of a bunch of numbers between 0 and 1, it goes rapidly to 0, but I'd rather it went the other rapidly to infinity. The Riemann hypothesis is equivalent to the hypothesis that log of the product of Farey fractions is equal to the number of Farey fractions phi of n minus 1/2 n plus an error term. So the error term is the square root of n. This is the usual way the Riemann hypothesis goes into problems. It goes in the size of the error term. So this theorem can be proved unconditionally with a bigger error term. But and n to the 1/2 plus epsilon is where the Riemann hypothesis goes in here. And if you had n to the 3/4 plus epsilon, then you get zeta function with no zeros to 3/4 and so on. Okay. So somewhere along the line, we realized that if you study Farey fractions there's a toy model that might be easier to analyze, and that's to study the unreduced Farey fractions, which take all the fractions in the unit interval, even if they're not in lowest terms. So we just take all the fractions, h over k, between 0 and 1, with both h and k bounded by n. And we throw out all the ones that are 0. And this is the unreduced Farey fractions. It also grows quadratically, but it's much simpler. So in the first case, we got the sum of phi of n, which grows like 3 over pi squared times n squared. It involves that number theoretic function phi of n is complicated. Here we just get 1 plus 2 plus 3 plus n, which is a binomial coefficient. So it grows like 1/2 n squared. Okay, so now we have the problem of studying the product of the unreduced Farey fractions. So the unreduced Farey fractions are, well, we can just write them down. The numerators are going to be j factorial for each j, and the denominators are going to be j to the j, and that gives us two numbers, n sub n and d sub n star. And the theorem is the reciprocal of this product exactly equals this binomial coefficient thing. The reciprocal of the product of the non-zero unreduced fractions is exactly g of n bar, the product of the rho n binomial coefficients. Okay? In particular, gn bar is an integer because of this. This, by the way, is very easy, and we actually sent it in as an American Math Monthly problem. I sent it in with Harm Dirksen a few years ago as a monthly problem that proved that identity. But what does it mean? Well, n sub n and d sub n are very large, and because of this, there has to be some enormous cancellation of the prime factors in d sub n and n sub n to reduce the whole thing to being 1 over an integer. Okay, and I should mention, of course, that the numerator is the superfactorial function, which is in OEIS, and the denominator is the hyperfactorial function, both of which have been studied at some length. As I said, the expression for the reciprocal of the unreduced Farey product. So I'm now flipping the thing over so you get it to be an integer. Okay? That's why I flipped the Farey fractions over also, because the unreduced Farey fractions are very nice when you flip them over. You just get the binomial coefficients. And we know that when we flip over this ratio of superfactorial and hyperfactorial, we actually get an integer, which means the expression that way is definitely not in lowest terms. But it's still nice. It's nice because dn and nn have very nice asymptotic expansion. And because of this, we can get a very good control over log gn, over the size of log gn. It will have a complete asymptotic series in powers of n. Incidentally, when we did this, I had to use the Barnes G function. And some unknown person claimed to me that you could manage to get this all just using the expansion for the log gamma function and not ever dragging in the Barnes G function, which is a more complicated object. Well, if that person happens to be in this audience, let me say, well, you should look at the constant term of that asymptotic expansion, because in that constant term appears the Glaisher-Kinkelin constant. And if you can manage to get the Glaisher-Kinkelin constant out of the asymptotic expansion of the gamma function, I would like to see that. But it does mean that we can get the following expansions, asymptotic expansion for the superfactorials and hyperfactorials. So everything above the constant term in the expansion you can just get using log gamma. And for this talk, that's all I need. You get log n factorial is 1/2 n squared log n minus a constant times n squared. And then there's a term that involves n log n. And then there's a term that involves n. And then there's a term that involves log n. And then there's a constant. And after that, you get 1 over n squared, 1 over n cubed. And there are such expansions for the superfactorials and the hyperfactorials. You notice that their lead term is 1/2 n squared log n. That's coming from the main. That's coming from the main term in the expansion. So And now, if we take their difference, we get a asymptotic formula for the binomial products. So the binomial products now have an asymptotic expansion that starts out with 1/2 n squared minus 1/2 n log n plus a constant times n plus an error that's a function of log n. Well, this is just by subtraction. But the point to be made is that the main term in the asymptotic expansions of the numerator and denominator cancel. The disappearance of the main term 1/2 n squared log n is the huge cancellation between the numerator and denominator and the factorials that's getting you down to a lower order term in this expansion. Okay, so we get something interesting out of this. Let's go to the relation between binomial products and prime numbers. So as I said, the main terms of the 1/2 n squared log n in both of the numerator and denominator cancel down to the main term 1/2 n squared in log of the unreduced Farey product. This is a lot of cancellation, and we knew it had to happen because 1 over gn is an integer, because gn bar is an integer. And this savings of a factor of log n is the same log n that occurs in the density of the prime numbers. The density of the prime numbers is n over log n up to n. And this log n savings is encoded here in this log n. And this is directly related to prime numbers. You can get a Chebyshev type estimate for pi of x, number of primes below x, right out of this formula. Now I want to rewrite this formula in a more suggestive way. It's actually a Riemann hypothesis. So you can rewrite this reciprocal unreduced Farey products in the form log gn bar as phi star of n minus 1/2 n log n minus 1/2 minus a constant times n plus a little o of log n term. And this formula has now been stated in a precise analogy with the Nicolas result. The Nicolas result, we have log of the inverse Farey products is equal to the number of Farey fractions, which is now replaced with the number of unreduced Farey fractions, plus a smooth correction, plus an error of the square root of n. Okay? But here we get something even smaller than the square root of n. We get an error that's actually log n. And in our context, what does this say? This says that there's probably some function attached to this thing that's playing the role of the Riemann zeta function. And this is sort of saying that function has no zeros in the critical strip all the way to real s equals 0. Now, for those who know, it's not zeros, it's poles, because in the approximation uses zeta prime over zeta. So here there's some function that has no poles in the critical strip all the way to 0. And that analogy is exact, but I won't show you the function. That's just warm-up, because another way to study things is to study the primes directly. So now I would like to go to the understanding the behavior of the oscillatory terms. So we're going to do the oscillatory terms, and then finally we're going to look at the product formula where we compare the oscillatory terms in the original part. So we have, in the paper that's posted on the archive, we give 3 separate formulas for ORD P of Gn. Now, actually, one of those formulas will be sufficient to explain the plots. But the reason we have several formulas is because the ultimate goal of this investigation is to understand what happens for the Farey products themselves. So the unreduced ones and the reduced ones are related by Mobius inversion. So you can get so that explains that the Mobius function is going to come in there when you do the inversion, and that's why perhaps the Riemann hypothesis turns up. So the more formulas you have for ORD P of Gn, they may come in handy later. So it's good to get them. These formulas are all, in one sense or another, they're related to the base P expansion of n. So now let me write n in base P as I equals 0 to k ai p to the I. The ai are the base P digits. They're between 0 and p minus 1. And the number of these digits is about log n. Log to the base P of n. So now, I need to introduce 2 well-known functions associated with the base P expansion. One is the sum of the digits. That's d sub p of n. By the way, there's no standard notation. There have been a zillion papers written on this, and they invented various different names for these functions. And I've also invented yet another name. D sub p of n. And then there's a running sum of digits in base p, which is the sum of the base p digits of j running from 0 to n minus 1. So it's the sum of the first n minus 1, the sum of all the digits in the base p expansion of the consecutive integers from 1 up to n minus 1. Okay, the n minus 1 is a convenience, but the literature did that, so I'm doing it too. Okay, so here is the main one of the three theorems, which says that the ORD p of the product of the binomial coefficients is 1 over p minus 1 times twice this running digit function s sub p of n, and then is minus n minus 1 times the base p digit expansion of n itself. So what this formula says is, it's got two terms. It's got a term which is an average sum of the size of the base p digits. That's this s sub p of n, which is a relatively smooth function. And then it has the sum of the digits of n itself, which in base p has, as you know, has an odometer-like behavior. A digit goes up to 0 to p minus 1. The odometer rolls over. You get some cancellation. And it's that d sub p of n, which is multiplied by n, that's producing the stripes that you're seeing in the picture. There's an s sub p of n that's giving you the big growth. And the second term is fluctuating strongly, and it's producing the stripes. And the first term is just kind of smoothly increasing. And there's a lot known about this smooth function. This first term has been analyzed in literature in the 1970s. It has a very interesting structure. It splits into two pieces. One piece is exactly n log p of n, and the second piece is negative, and it has fractal properties, and it's related to the Riemann zeta function, and it's a smaller growth, O of n. I'm going to show it in a minute. The second term, on the other hand, has, on the average, half the size of the main term. So the main term is n log n. There's this correction, little o of n. And then there's this second term that's being subtracted off from the base p digits. And on the average, it has size exactly half the main term. Okay? And we can analyze it completely, because if you pick a random number and you look at its base p digits, each digit separately is drawn from a binomial distribution with peak at p minus 1 over 2. You pick 0 to p minus 1 with equal probabilities. And we're adding log n of these things together. So we're getting a central limit theorem on the whole thing. Which, so if you draw randomly, it's sharply peaked, but it's very strongly correlated if you vary n in a straight line because of this odometer behavior. Nearby values of the dpn are related. And here's a precise version of this assertion about s sub p of n proved by Delange in 1976. He proved that sp of n is equal to exactly p minus 1 over 2 n log n plus f sub p plus a function which is a continuous real-valued function periodic of period 1. And this function is known to be continuous but everywhere not differentiable. And you evaluated it on a logarithmic scale. So there's a f sub p of log p of n. And the Fourier series is the plot of f sub p of n is f sub p of n is non-negative, is strictly non-positive, and it takes the value 0 at one endpoint. And actually, this theorem is not just for prime bases; it's for all bases. Okay. And here's a plot of f sub 2 of n. So f sub 2 of n, as I said, is 0 it's periodic at period 1. It's negative, it's non-positive, and enough is known about it to prove that it's non-differentiable at every single point. A lot is known about its smoothness. And f sub p being periodic at period n and this log n variable means it has a Fourier series. And Delange computed its Fourier coefficients exactly. And these Fourier coefficients include the values of the Riemann zeta function on the line real part of s equals 0 at the points 2 pi ki over log p. And I want to say those are exactly the locations of the poles of the Euler factor of the Riemann zeta function at the prime peak. So that's why those values are getting picked out. Now some things you can get out of this formula and the two other formulas that I'm not shown is you could prove that order P of Gn has minimal value 0, and this is attained at P to the k minus 1. This is a very well-known result in binomial coefficients that at level P to the k minus 1 in Pascal's triangle, P never divides any of the binomial coefficients. And the maximal value you can now bound by this formula exactly. Or P of Gn is less than n log P of n. And we got that because it's exactly equal to n log P of n minus plus 2 terms, each of which is non-positive. And in fact, here you don't attain the bound exactly, but you get very close. You get within log P, n log P of n minus n, which is attained at powers P to the k. Because of this, you can get a Chebyshev bound for the prime number of a prime number type out of this rather easily. We have now an upper bound for each GP of n, which is n log P of n on the nose. There's no error term. So if we plug this into the formula for log Gn bar, which is equal to GP of n times log P, well, log to the base P of n times log P is exactly log n. So every one of these terms is exactly bounded by n log n, and there are pi of n of these terms. So the sum is bounded above exactly by pi of n log n. On the other hand, we have a complete asymptotic expansion for log Gn bar that starts out 1/2 n squared plus an error. And the error term is completely controlled, so you can get rid of it and you can plug it in there, and you get pi of x. You just plug in 1/2 n squared, and the second term of the error thing has a minus sign, so you can get rid of it eventually, and you can prove that pi of x is greater than 1/2 x log x by this formula, which, by the way, is a terrible estimate for pi of x. And Chebyshev got 0.9 times x over log x. So why are we bothering with this? Well, first of all, this theorem works all the way down to 3. And if you check it at 3, it's pretty good. But there's another reason. And this is very intriguing, I claim. We know that the digit sums are sharply peaked around p minus 1 over 2. We haven't used any information about the digit sums in this. We just threw away. We had a main term, which is the term coming from Delonge theorem, which is n times log p of n, which is exactly twice the average size of the behavior of this function. The bottom side is oscillating, and it's of half the size on the average. So if it were the case that you could do the average, we now have a sum that in this product that's an average over all the primes p up to n. If we believe that when we did that averaging, each one of those contributions was half the size, then we would get the prime number theorem on the nose by this method. If you could do an averaging where you fix n and you let p vary, you would save a factor of 2 and you would get the prime number theorem. But what we know in the distribution of digit sums is we get that average if we fix p and we average over n. But here we have interchanged the averaging. We are now averaging over, fixing n and averaging over p. And as usual, interchanging limits like that is a big mess. And not only that, in this case, you can't do it. The averaging does not work. You're still going to get the same answer, but it's not coming from this behavior that it converges to limit. So it's an interesting thing to investigate further. So now I want very briefly to say some stuff about Farey fractions. So that's what I have to say about the unreduced fractions. And now this is the real stuff, the Farey fractions. So the Farey product is the product of the Farey fractions. Here are the inverse Farey fractions. You will notice they're integers for a while, and then f7 is not an integer. It might not have been computed correctly here, but it's not an integer. And in fact, you can show that only finitely many of these Farey products are integers, and the last one is n equals 50.